for starters, so here's our mechatronics system diagram. We're to the point now where we want to make things do stuff. And we already started that a little bit. You put servo motors on your robot and you're controlling servos and getting your robot to drive around and do things. So that's a good first step. We're going to introduce a wider variety of actuators today and in the next lesson. Today we'll mostly be focused on electromagnetic actuators, specifically DC motors, but we'll talk about, next lesson, we'll talk about some more interesting, not necessarily more interesting, but some more novel, I would say, types of actuators, piezoelectric actuators and shape memory alloy actuators. They will also talk about stepper motors and other types of actuators there. Okay, so first of all, these are the various actuator types, and the ones highlighted in red are ones we will directly talk about in this class. I want you to be aware.
Excuse me.
Yes.
I'm not sure if it's just me, but all right, now I just got the slides. Sorry, I wasn't seeing the slides, but I see them now.
Okay.
Sorry about that.
Yeah, no problem. Thank you for warning me. Okay, so I've tried to give you an outline of various types of actuators out there in white, but the red ones are the ones we will directly talk about. And we'll jump right in here with some the simplest type of electromagnetic actuators. Before we do that, all the actuators we're going to talk about today, we're going to talk about solenoids, we're going to talk about DC motors and brushless motors. They all follow the same principles of electricity and magnetism. And you may remember this from physics, but if you have a current, basically charge moving in the presence of a magnetic field, a force is generated. You can also generate a magnetic field with a moving charge or a current, right? So the right-hand rule for that is shown right here. If you can see my hand, can you see my hand all right?
Yes, sir.
Okay, so if you put your fingers in the direction of the current and then you rotate them with your right hand in the direction of the magnetic field, your thumb will point in the direction of the force being generated. Okay, so the force is I cross B. So we'll see that in action here in a couple different ways. Okay, so the first type of electromagnetic actuator I want to show you is the solenoid. Oh, wait a second. Oh, I shouldn't have done that. Someone's chatting me. Cody, no, your pre-lab will still be due on Monday. You need to have the pre-lab done in order to do. My intention is not that you work on lab 6 during Monday's lesson. I want you to be starting lab 7. What we will be doing is I want you to have the opportunity to show me the various parts of lab 6 or get help on things that aren't working. So your plan going in, look, it's like, it's a zero-sum game. There's only so many lessons. If I could give you another lab day, but I'm just taking away time from your final project. And I've never had a cadet in all the years I've taught this tell me, I wish we had less time on the final project. If you get my drift. So I want to stick to the schedule as it is, but you know, you can be working both lab 6 and lab 7. Okay, good question though. Good question. All right, trying to reshare my screen here. There we go. So taking you to a cool animation that I think is very helpful in understanding how a solenoid works. But basically a solenoid is a coil of wire that we run a current through and a magnetic field is created. There is usually an iron core device in the middle of the coil that is then affected by the magnetic field that's generated. So here, if I turn on the current, now we can use the right-hand rule and basically wrap your fingers in the direction of the coil wires, in the direction of positive current flow, and your thumb will tell you the direction of the magnetic field that is generated. So in this illustration, if I wrap my fingers around those coils of wires, the magnetic field should go to the left. And so if I turn up the voltage on this guy, we see this green arrow indicating the magnetic field and moving out to the left. Okay, so if there's something inside that coil of wires, it's going to be, and it's a ferrous material, so it's magnetic. It'll be shot out that coil of wires. And that's how a solenoid works. If we reverse the current direction, then the magnetic field will go in the other way, and the plunger would go the other way. Okay, so solenoids are used in magnetic or electric door locks in your car to engage your starter motor to your flywheel, things like that. Solenoids are great when you need a small range of motion, linear motion, where you just want to move, and weight isn't a big factor. They tend to be fairly heavy, but if you need a high force and you just need a short range of motion, they are great for that. So that's how a solenoid works. That's as much as we'll talk about solenoids, but the same electromagnetic principles apply to numerous types of actuators. Okay, so let's talk electric motors. There's a number of different types of electric motors. Some of the first electric motors were AC, alternating current. And those come in two major types, synchronous and asynchronous. Then we have DC motors, which are probably, you're probably more familiar with if you had experience playing with motors. So back me up a little bit. AC motors are most often used in industrial applications. They tend to, the benefit of AC motors, and we'll talk about them a little bit more here in a second, they can draw power from the wall, which is alternating current, and you can get rotary motion with very few moving parts. You don't have to have lots of interacting parts, as we'll see with your standard DC motors. They have parts that can wear down. AC motors avoid that problem. They're limited in their speed they're able to do, or the variability of their speed, but they're really useful for various industrial applications. And if you went out and walked around the Mech lab, you would find lots of AC motors. Your drill press is running on an AC, probably asynchronous motor, a ceiling fan, AC motor, very simple, easy to manufacture, not a lot of complicated parts. Okay, so DC motors come in two types. We have two major types, permanent magnet, and these are usually going to be less than 5 horsepower. And so with permanent magnets, they can be brushed motors, which is what we'll mostly talk about today. That's probably what you're most familiar with. Or you can have brushless, which are a more recent technology. That's what's used in, for example, in quad rotors. They're high efficiency. And we have stepper motors. Then, so what distinguishes these types of motors is that they have a permanent magnet, meaning, which is what it sounds like, a magnet that is permanent. It doesn't move, it doesn't change, and that interacts with a field, with electrical windings and the magnetic field generated by the current flowing through those wires. Okay. On the other hand, you could have what's called a wound field motor. And with wound field motors, we'll talk about those next lesson, you have two sets of coiled wires, and they're both creating their own magnetic field, and those interact together. And so with wound field motors, there's a couple different types of those. There's shunt, also known as parallel. There's series, and there's compound wound. And we'll talk about what all those mean and the various characteristics you get from those different designs. So each of these three designs have different strengths and weaknesses, and so give you a different type of behavior for the motor. Okay, so the first type of electric motor we'll talk about is first, I guess we're not doing that. First, we'll just talk about some simple terminology. This is an example of a permanent magnet DC motor, but the terminology is generally applicable to AC motors as well. You have something called a stator and something called a rotor. Stator, it comes from the word stationary, so it's the part that doesn't move. So in this example, the center core is the rotor, and that's what's going to spin when you run the motor. There are windings. In the case of a DC brushed motor, you have what's called a commutator, which is these gold parts in the middle, and brushes that transmit current from the power source to the windings of the motor. And we'll talk about how that works in a moment. Okay, so in general, how does an electric motor work? Well, so we've talked about electricity and magnetism and how those interact. So starting over here on the left, if we have a permanent magnetic field here generated by north and south poles of magnets, the magnetic field line is running from north to south. And then we have a wire, and we pass current through the wire. The right-hand rule tells us that, so you put your fingers in the direction of the red arrow of the current, and then curl your fingers in the direction of the yellow magnetic field line, and the thumb will tell you which way the force is generated. So a force would be generated that would tend to push that wire upward. So if we take that wire and we put it into a coil, as we see here in the middle image, if the current goes in the bottom and out the top, we'll get a force pushing down on the coil on the right and up on the coil on the left. Of course, that is a torque, and so that coil will spin until it is lined up vertically. And that, at that point, it would be in a neutral position. It would want to stop. Can everyone see these diagrams and understand what I'm talking about here? This is kind of
Yes, sir.
point, so I want to make sure you're following me. So I heard Kevin say yes. Sean, you follow me?
Yes, sir, I am.
Okay, great. Okay, so now if we go to this diagram on the right, we see, in reality, we would want more than one coil. So if we put several coils in here at any one time and we connect them together, at any one time, we can get a force that's going to continue to rotate the motor about its axis. Now, the problem is when that coil gets lined up vertically, it has no force on it, and it would want to resist moving any further. So at some point, we have to switch the direction of current through the wires or somehow change the way the magnetic field is working. And the various types of motors are basically handling that function differently. How they either switch the direction of electricity or switch how the magnetic field interacts with the rotor. And so we'll talk about those various designs in the coming slides here. Okay, so back to AC motors. The first, so we have synchronous, which is similar to a permanent magnet DC motor where you're actively changing the direction of current as you as it spins around. I think a simpler type of motor and more prevalent and more relevant to you guys is the AC induction motor. And okay, so we'll look at an animation of how that works here in a moment. So with an AC induction motor, in the example we'll show, there will be a rotor in the middle, and it has it just sits on bearings. We don't actively transmit any current to it. Current runs through the outer stator of the motor, which will have the windings around it. So there's no current or magnet in the rotor itself. Instead, there's a rotor that has a part known as a squirrel cage, and the squirrel cage has a magnetic field that is induced into it, and that's where we get the term induction from. We need to have a 3-phase power source in order to have an induction motor. It depends on that, having a 3-phase power source. So 3-phase AC. Now this is not what comes out of your typical wall outlet. You don't normally have 3-phase, but in industrial applications, it's very common to have those types of outlets. So we have a number of them in the Mech lab. So here's what 3-phase would look like. You'd have basically, sine waves. And you have they're all 120 degrees out of phase. So I'll do my best to draw this. So something like that. I think this is perfect. Obviously, I've got my amplitudes off. So normally they would all be the same amplitude, but they're 120 degrees out of phase. So that's the term 3-phase. As these, so the outer stator of the motor has 3 different sets of windings, and they're each carrying one of the phases of the 3-phase power. And as those currents are flowing through those wires, you're getting changing magnetic field. So show you a helpful video here that this video will animate how this works much better than I could possibly explain it. Make that full screen. Okay, I assume you cannot hear the sound from this guy. Can you hear that?
It was super quiet. It was cutting in
Okay.
and out too.
I'll just mute it and I'll just narrate for you. Okay, so so you see the brown here, the brown or gold, those are the windings. So those are the wires. And there's 3 sets of them, and they're each getting their own phase of the current. But that current is fluctuating, it's alternating current. So as it's alternating, there's this magnetic field that is created that's rotating around the axis of the motor. And that's what's being shown by these these yellow field lines. When you have three phases here, so showing you the three phases and that they're going up and down. They're all going up and down differently. So at any given point in time, even though these outer windings do not move, they're stationary, but because it's alternating current, it creates the effect of a moving magnetic field. So you can see that the blue lines indicate how the current is changing in the wires, and then the yellow lines are indicating that how it's moving, it's creating a rotating magnetic field. Okay, so then the center of the motor has a core, and that's what the rotor is. So this is called the squirrel cage, and it's designed very carefully. Those angled slots are intentional. We know from physics that if you have a changing magnetic field, you will induce a current. So there's current flowing through these different sides of the squirrel cage, and they're saying they put these iron cores inside the squirrel cage that helps improve the magnetic performance. But basically, a magnetic field is being induced in the rotor itself. So now you have the external magnetic field that's generated by the electricity we're passing to the windings of the motor, and then you have this induced magnetic field inside the rotor. And as long as those things are slightly out of sync or asynchronous, you'll have a torque that results from those magnetic fields being misaligned. So what is that the speed of the rotor, that's what N is here, will always be a little bit slower than the speed of the external magnetic field rotating around the external stator of the motor. And this video just goes into more detail about how that all works. So your takeaway for this class is that you have an asynchronous motor is a way to get rotary motion that's very simple. You saw that there's very few moving parts. You just have that rotor, and the rotor would be supported by some bearings. But there aren't the more complicated, intricate parts that you get in a DC permanent magnet motor. So, kind of benefits of a three-phase AC motor is we get very simple, no moving parts. They're inexpensive and very efficient. Now they're not very miniaturizable. Okay, so if you're thinking about,
Sir,
yes.
when you say very efficient, like what percentage efficiency would that be?
I don't know.
Okay.
That's a great question. Very good question. And I'll look that up after class. Good question. I'm sure we could Google it and get a pretty good answer. Okay, drawbacks is you need a three-phase power source. And I bet Mr. Rodin could tell us a lot about those types of motors, but I won't put him on the spot. Okay, we're going to move on to DC motors. A new blank slide here. Okay.
Sir, could you bring the notes back up? When you were writing them down, nothing happened until just a second ago. So.
Okay. So I was just making these notes about pros and cons of the three-phase motor. Did you catch that?
Yes, sir. I was listening to you as you were talking about it. I just I
Yeah,
missed
no,
the
no,
last
sure, no problem.
Thank you.
Okay. So let's talk about permanent magnet DC motors. So we're going to draw a circuit diagram. So you've got some voltage source. It's got, the motor has windings, and the windings have the properties of having resistance and inductance. So these are like windings. We have an L, we have R. Then we've got, here's where the magic happens. There's some rotor and a shaft, and we hope that we're getting some torque from the motor as a function of time and some speed of the motor. And current has to go in a loop, so it goes back to the voltage source. Now this rotor has to be in the presence of a field. And I mentioned that field could be a permanent magnet, which is what we're going to talk about now, or it could be another magnetic field generated by another coil of wires. Okay. And we hopefully have current flowing through the loop. Okay, so here's, for your viewing pleasure, a simple DC motor. You have something like this in your toolbox. Okay. Hopefully you played with one of these before, you know, when you were younger or something, or maybe a high school science class or something, or just messing around. So if I just put some power on that motor, it'll spin. Very straightforward. Obviously, so battery, what current source is it? AC or DC?
DC.
DC. Okay. So that's a very simple motor. You've got one of those in your toolbox. This one's a little bit more complicated, just in that it's a bigger motor. It has a gearbox attached to it. That's what this part is. So you notice when I hooked up 9 volts to this, it spun pretty fast. We'll see that how fast it spins is directly related to the voltage that you apply to it. In general, DC electric motors want to spin very fast, so it's common to have a gearbox on it to slow it down and create more torque. You know, at this speed, you're not going to get a lot of torque out of this little motor. I could probably easily just stop it with my fingers. I can. You know, it's very easy to do that. So this motor is going to go slower and a lot more torque. So this one, it's really a lot harder for me to slow it down just by pinching on it, because it's got that gearbox on the top. The other thing this motor has is on the back, it's got a rotary encoder, and this one actually works with a Hall effect sensor. So we briefly mentioned that in the sensors lesson. Hall effect is just another type of magnetic sensor. I know some of you who researched Hall effect for their sensor homework. I know somebody did.
Sure, I think it was me.
Okay. Do you remember anything about Hall effect? You want to tell your classmates?
I remember there was it worked off of the proximity to an electric field. So it's used in phone cases and stuff. So it senses that electric field, and then it either sends voltage or whatever to create an action.
Okay, good. All right, so that's how that sensor works. All right, so how does we want to dig into these DC motors a little bit more and learn about how they work. You know what? Let me the mathematics behind it. I want to back up and look at the slide, the diagram of the DC motor. Okay, so I've talked about how we have to have a way to switch the current so that when that coil of wires gets lined up between the magnets, we need to switch the direction of current. So, you know, back to this diagram, if we just had the single coil, and if current is going through in this direction, see this red arrow I'm adding on there, it's going to want to rotate that coil until it lines up vertically here. And at that point, it's going to want to stop because the forces will be balanced between the top and bottom coils. Well, so if we switch the current at that moment in time, then we'll get an attractive force here that wants to pull that coil that way, and we'll want to pull this coil that way. So we need a way to repeatedly switch the direction of current through the wire. So we do that with the commutator and brushes. So down here, this is the commutator. And you'll see it's got a slit in the middle of it. So there's it's basically two semicircles with a gap between them. And then we have these brushes, which have the current carrying wires attached to the brushes. So these are brushes. And they're called brushes because they brush the commutator. And they're usually something like graphite, like you'd have in pencil lead. And they use graphite because graphite is conductive, but it's also low friction, relatively low. Okay, so they will just be pressed lightly against the commutator. And we see that the coil in the winding is attached to the commutator. It's electrically connected. So in this orientation, current is flowing in to the commutator on the right, and that's providing positive current going in this direction and out that brush on the top. As this winding rotates, this slit is rotating also, and when that coil is oriented vertically, now this commutator, the one we could call the left, it will now be in contact with the closer brush. And in doing so, the current will reverse direction. I hope that explanation made sense to you. Let's take a look at the next diagram that has a little bit more, the previous diagram is a little bit more detailed. So here in this diagram, hopefully it's more apparent that the commutator is not one solid piece. It's two halves. And one half is connected to one set or one end of the coil, and the other half is connected to the other half of the coil, the other end of the coil. And as the rotor spins, the brushes are alternating contact with each half of the commutator. And so that's what reverses the direction of. So what's nice about this design is I don't need any kind of sophisticated control algorithm to run this motor. I just simply attach a DC power source to it, and it will start spinning because the commutator is mechanically changing the direction of current. With other more sophisticated motors, we have to do that directly, specifically with control electronics. That's how a brushless motor works. Okay, so with a permanent magnet motor, it's mechanically changing the direction of current through the commutator. Okay, so let's look at electrical behavior of this. So we could analyze this circuit using Kirchhoff's voltage law. So let's do that. So the first thing we see is the power source, V of T. Then we subtract I times R, the voltage drop across the resistor. Voltage drop across an inductor, in case you don't remember, L di dt. So it's proportional to the rate of change of current. Then we have what's called the back EMF. And this is, EMF stands for electromotive force on the slide. That's the, it appears to us as a voltage that is generated by the motor in opposition to what we're trying to do. You could think of it almost like a resistance to motion, but it's in the form of a voltage. And each motor will have a back EMF constant, K sub E, which is also known as the speed constant. And it just depends on the design of the motor. So all of that then equals 0. So that's our KVL for the motor. Now, if we assume, or if we're trying to predict the motor's behavior at steady state, what does steady state mean?
It's like a constant speed rotation.
Yeah, constant speed. So in the example I've been showing you, if I take my small motor and I attach my 9-volt battery and let it get up to speed and then maintain that speed, I want to predict what its speed will be at that 9 volts. I'm analyzing it for steady state operation. So for steady state, I can eliminate the LDIDT term, and that simplifies our equation. So then we get V equals IR plus K sub E omega. Now, in addition to the speed constant, or the back EMF constant, we also have what's known as a torque constant. And the torque equation. And that is that T equals K sub T I. Now, what's really cool, one of the neat circumstances of physics is that KT and KE are actually equal if you get into SI units, proper units. So KE will have the units of, well, I should ask you, given this equation here, that the EMF, the back EMF voltage equals KE times omega, what would the units of KE be?
Newton meters over amps.
Newton meters over amps. Well, that would be KT. So we'll jot that down. Thank you, Adam. KT would be in units of Newton meters per amp. What would the units of KE be?
That'd be volts per radians per second.
Very good. Volts per radians per second. So if you get these in the same units, these numbers, so if you have these in these units, the numerical value should be the same for those. So that's kind of cool. Okay, so back to our equation here. So torque equals KT times I. I want to solve this. I'm trying to get an equation that can relate torque and speed of the motor. So if I substitute that in there, I'll get B equals CR over K sub T plus KE omega. And I'm going to rearrange this to get torque equals K sub T over R times V minus KT KE over R times omega. And the reason I put it in that form is this is the equation of a line. And now we can plot this, and we're going to do that. So similar to how we did for transistors, we're going to create a load line plot. So torque and speed. And this is a linear equation because we're assuming steady state. So that makes it a little easier on us. So we'll have some sort of line that looks like that. So what I'm showing on this slide is, this is a rehash of what we just did. We started with this KVL equation. We assumed steady state and simplified it to this. We introduced the torque and current terms, and then simplified this to this torque speed or load line equation. And that's what's shown here. So what this is indicating is that for a given motor at a given voltage, there we go. So say this is like 9 volts. You'll have this line, and your motor will operate at some point on this line. What we're doing here is we're trading speed for torque. So when I just threw this motor on this battery, it's gonna, right now it's running at its maximum speed because there's no load being applied to the motor. Let's show you the motor, okay? I do have this little piece of tape which is creating some drag, so that's some torque. So I could take the tape off and it might spin a little bit faster. If I put a load on the motor, meaning it's going to slow down. Okay, so as I load the motor, it's having to generate more torque, and as a consequence, it's going to slow down. So its operation will ride up and down this line depending on what the external constraints on the motor are. If I wanted it to, so at no load, we call that the no load speed. That's right here. Omega sub NL is this is no load speed. No load. That's this point on the curve. That's the fastest it will ever go. If I wanted to go faster, what could I do?
You could just
Increase the voltage.
I could increase the voltage, up to the safe limit of that motor. Okay, so it can increase the voltage and get it to go fast. But for a set voltage, this is as fast as it will ever go. This point is the stall torque. That means the torque at which the motor will stop spinning. That's the maximum torque you could get. Again, if you needed more torque, you could increase the voltage and get more torque. Okay, so down here are some various performance equations for motors. So stall torque, we can calculate the no load speed or the stall torque by taking our torque speed equation and zeroing out the other one. So we know that the no load speed happens when t is 0. So if we set t equal to 0 and solve for omega, we would get this result here. If we want the stall torque, we set speed to 0 and solve for torque, and we get that stall torque there. Power is defined from physics as torque times speed. So for a motor, it's torque times angular velocity. We get max power at the middle of this plot. Okay, so wherever half T stall is right there, half no load speed is right there, and that's where we get max power for the motor. So your maximum power output will always be halfway between its 0 and its no load speed. Now max efficiency, or what the actual max power will be is a quarter of those terms multiplied together, okay? And that's the equation for that. And so where is it most efficient? Well, it's most efficient usually to the right of the max power point. And your textbook has some plots that indicate that. But the reason for that is that your permanent magnet DC motors would rather run very fast at a low torque than go slow at a high torque. That's because when you're doing that, when you're running your motor, your efficiency, you're trading off electrical losses in the coil of the motor against friction in the bearings. And running faster when you run slow, you're drawing a lot of current, and so resistance in the windings is very high, and that is more dominant than friction is. So in general, you want to run at a lower current and a faster speed. That's why we put gearboxes on DC motors, so that the motor can spin fast, and we use the gearbox to step it down to a slower speed with a higher torque. Okay, let's look at an example problem. So we have a permanent magnet DC motor with the following specs. What is the available output torque? So we're given a torque constant, we're given resistance, and TF, this is friction torque. So that's just something we'll subtract out later. So the available output torque the total motor torque, TM, is a sum of friction torque plus the load torque or the output torque. Okay, so we want to know in this case what's the torque available for the load, and so that's going to be the motor torque minus TF. What's the motor torque? Well, we can use, oh, that's supposed to be covered up anyway. So the motor torque, we use our motor equation, but we're assuming if we're maxing motor, that would mean that the speed is 0. So we can zero out this term, and so that will just be KT over R times Bn. And so in this case, that's 5.89 inch ounce per amp over 1.76 ohms times 12 volts. And if we crunch the numbers there, we'll get that TM is and then subtract, I don't have the intermediate answer there. Well, we'll get T of motor is 40.2 inch ounces, and then T available for the load or for the output will be 40.2 minus 1.2 or 39 inch ounces. Okay, so it's very straightforward, these types of problems. Okay, they're linear equations. They're straightforward, pretty simple. Okay.